Hi, it's Andre from High Performance Academy and welcome to this webinar. We're going to be focusing in this webinar on PID tuning and also feed-forward tables, and specifically we're going to be relating this to the MoTeC M1 platform. Of course, PID tuning is applicable to a range of platforms though, so it does go a little bit broader than just the MoTeC M1 platform, and it's really essential knowledge for anyone dealing with modern programmable aftermarket ECUs. So let's start with what we're actually talking about with PID tuning. Really what we're referencing this to is closed loop tuning. So any aspect where the ECU is trying to control a particular output in order to achieve a certain aim or target. That on itself probably doesn't sound overly it's not an overly good explanation, but what I'm talking about here is a range of aspects that the ECU controls. So for example, boost control is a great one. Obviously we use PID there. We are trying to control the wastegate duty cycle or wastegate actuator. That's the output that the ECU is controlling, and we're trying to control that wastegate in order to achieve a specific boost target. So that's a really common example of PID. Other aspects that the ECU is in charge of where PID is utilized though is something as simple and common as idle speed control. Also, we could look at drive-by-wire throttle control where we're trying to accurately control the throttle butterfly position. And of course another one is variable cam control. So any of these aspects that the ECU is in charge of where we're trying to control a solenoid or an output that the ECU is functioning in order to achieve a specific target. Now, in my experience, this is an area that most tuners really struggle with. They don't really understand what PID is, and it can seem scary. And the problem with this is if you don't understand how the PID control algorithm functions, it's very, very easy to get yourself so far away from the correct numbers for your particular system that the control is absolutely abysmal, and it's almost impossible to find your way back to a set of numbers that is actually going to give you good control. So like anything with tuning, being able to get good control with any PID control system requires some intimate knowledge of how the PID control algorithm works in the first place, and that's what the task of this webinar is. Before we get into PID control, I just want to cover the two terms open loop and closed loop control, because these become quite important to PID tuning. So when we're talking about open loop, in this situation the ECU is just blindly controlling an output and doing whatever we tell it to do with that particular output and completely ignoring any feedback on the result of that output. So if we liken this again to boost control, this would be where we are just supplying a fixed duty cycle to the wastegate irrespective of the actual boost pressure that we're achieving. Now that can work to a degree, but again I'm going to reference most of my example today on boost control just because it's going to be really easy for me to give you some practical demonstrations here on our dyno, but of course they are applicable to a wider range of PID control tuning, so don't think it's only relevant to boost control. So coming back to our boost control example, if we're using open loop control, we're just supplying a fixed duty cycle to the wastegate, and that might get us somewhere close to the sort of boost pressure that we want, but the problem is depending on perhaps atmospheric conditions, what gear the car is in, hence how much load is being applied, even the temperature of the exhaust gases, exhaust manifold and turbocharger, these will all result in different levels of boost, so it's very difficult for us to get a nice solid fixed boost level irrespective of the operating conditions. That's where closed loop comes in, and with closed loop, what the ECU is actually doing now is looking at our desired or target boost pressure. Then it's also looking at the boost pressure it has at any particular time, and based on the error between our target and our measured boost pressure, it can then adjust the duty cycle being sent to the wastegate in order to get us to our target. So in this situation, the ECU is able to account for those changes I just talked about. We should properly set up, we should be able to get really accurate and stable boost control irrespective of our operating conditions, irrespective of our atmospheric conditions, etc. So if we want to achieve really stable and accurate control, then closed loop control is really important, and this is where our PID control algorithm comes in, because the PID control algorithm tells the ECU what to do if there is an error. So that's really essentially what we're talking about here, how the ECU can cope with an error between our target and our measured set point. Again, that may be boost pressure, it may be cam angle, or it may be idle speed or throttle position, any control that the ECU is functioning. Okay, so as I've said, we are going to be talking about boost control. It's important to understand that our PID control needs to be tuned and set up dependent on whatever we're trying to control. So we can't come up with one set of P, I, and D gains, and I'm going to talk about what those terms mean really shortly, and expect to be able to apply those to every ECU and every control task that we're trying to set up. For example, if we looked at idle speed control versus cam control, the speed at which the engine RPM changes when we're looking at idle speed control is much slower than how the cam control can move. Likewise, the sort of error that we're probably happy to accept with our idle speed control is probably much different than what we might expect or accept with the likes of drive-by-wire throttle. For example, if our engine RPM is 50 RPM away from our target, probably the chances are we're not going to be too concerned about that. But when we're talking about drive-by-wire throttle control, we need to be very precise to perhaps 0.1% or even less. So the control setup, the way we tune the algorithm, and the numbers that we use are very dependent on the type of system or type of control that we're actually trying to tune. Okay, we need to start with the term feed forward, because this is actually the first place we start with our PID control tuning. And feed forward is a term that MoTeC have introduced with the M1 platform. For those users transitioning from the 100 series, this is the same as what was referred to as the normal position table. And we also may hear terms such as base duty cycle or something of that nature. And essentially what the feed forward table is simply a table of our base duty cycles that are going to be applied to the particular control to get us close to our target in open loop. So again, using my analogy or my example here with boost control, these are the base wastegate duty cycle percentages that are going to be sent out to our wastegate solenoid that are going to try and get us very close to our boost target before any closed loop control is functioned by the ECU. Now, the reason why we want to do this is it gets us very close to our target without any closed loop functionality, and essentially the less work the ECU has to do, so the smaller our error is, the better our closed loop control is going to be. So this is an area that's really commonly overlooked. It's almost impossible to achieve really good, really stable closed loop control of any system if our feed forward table is incorrectly tuned in the first place. So this is where we're going to start. At the end of this, once I've described all of the terms, I'm going to go through a tuning strategy that you can apply. So we will actually talk about the steps in a little bit more detail, but this is where we want to start. We want to get our feed forward table correctly tuned so that we're already really close to our target before we actually bring in any closed loop control. Okay, now we're going to move into the PID part, and I find the easiest way of explaining this is through a real-world analogy, and I'm going to go through this analogy, which actually comes from Mark McCoy at MoTeC in the first instance anyway, so I'll credit him with this analogy. This was like a light bulb moment for me, and I hopefully it will be for all of you watching this as well, because if we go through the technical terms of P, proportional gain, I, integral gain, and D, derivative gain, on their own it's really hard sometimes to piece together and figure out how they actually interact and what they mean. So a real world analogy makes it much easier to see how they actually work. So we're going to go through this analogy, then we'll go into a more technical breakdown of what each of the terms means. So let's say that we have a flat piece of road and we've got a car sitting on the road, and 100 meters away from us we have a line on the ground. Now what we want to do is we want to accelerate our car and we want to stop it right on that line. Now the problem is, in our first instance, the only control that we have available to us is the accelerator. So obviously if we want to get up to that line really quickly, we're going to use a lot of throttle. But remember, we only have the throttle at this instance. So once we start rolling and we back off the throttle, if we're going too fast, what we're going to do is overshoot the line. Once the car comes to a stop, then we're going to have to select reverse, apply throttle, and this process is going to be repeated as we go forwards and back past the line until finally we end up sitting straight on that line. This is where we want it to be. This is our target. So the throttle in this analogy is our proportional gain. So the harder we press on the throttle, the faster we're going to get up to that line, but of course we risk overshooting the line and then we're going to have to reverse up to get back to where we wanted to be. Now let's add into our analogy the brake pedal. So the brake pedal in this case is our derivative gain. So now what we can do is use a large amount of throttle initially, and as we approach the line we can start applying the brake, and this is going to let us get up to the line much more quickly without overshooting the line. So that's how the proportional and the derivative gains combine. Now, of course, we can use different amounts of both the proportional and derivative gains in order to achieve the best possible results, and we'll look at that a little bit further through the webinar. Now what we're going to do is we're going to assume, rather than our piece of road being flat, it's now on an incline. And what we're going to do is introduce our third term. In this case, what we're going to do is now allow the driver to use the handbrake. And this really references the integral gain component, and this is going to allow us to hold the car steady on our set point on this incline. So that gives you some sort of real world analogy of how all of these terms work. Now what we're going to do is we'll just go through and look at these terms in use. So let's just jump into my laptop now. I'm going to go through a series of slides here showing proportional, integral and derivative elements being used together. So what we've got here is, on the vertical axis we have our position, our aim point, whatever we like to call that. I'll just try and get rid of that. Okay, that's working. Hopefully this is going to play the game. So here we have our aim position in red. So this is what we want to achieve. Now in our first example here, you can see what we've done is we've applied a small amount of proportional gain. We've left our integral and our derivative gains purposely at this stage at 0, and our blue line here represents our actual measured position, whatever we're trying to achieve here. Let's say in this example we're talking about drive-by-wire throttle control. Okay, so we can see that with a small amount of proportional gain, we haven't actually been able to get to our target. We've got quite a large error represented here between our measured and our target positions. Okay, so what we're going to do is we'll move to our next slide. In our next slide, what we've done is we've increased our proportional gain compared to our first attempt. And you can see now two aspects. First of all, we can see that the measured position rises a lot more quickly towards our target. We can also see at the same time that we are now closer to our aim position, but of course we still have this error present. So we're getting closer. What we're going to do now is we'll just move to our third slide. Just get rid of these. Go to our third slide. And now we've added even more proportional gain. And what we've got now is a very quick track of our aim position. However, what we can also see at the same time is now we've actually overshot. We've gone past our target, we've exceeded our target, and this has resulted in this small amount of oscillation before the system has settled down. So that's not particularly desirable. We're closer to our target yet again, but we also still have a small amount of error present. Just let me get my drawing program back up and running. We've got a small amount of error still present, which you can see. So we're getting much closer, but we've got two problems. We've still got a little bit of error, and now we've got this overshoot or oscillation. Let's move on to our fourth slide. And what we've done now is we've added in some derivative gain. Now, our derivative gain, remember, that's our break. And what we can see is now we do still have some oscillation present, but it's much smaller than what we had with just proportional gain on its own. You can see that we still have a small amount of error remaining. So from here, what we would now do is reduce our proportional gain slightly, and that's going to reduce this overshoot even further. And then to deal with this remaining error that we have here, we're going to add in a small amount of integral gain. And the integral gain is there to help fix any remaining error relative to time. Now, what we want to also do is have a look at how the proportional, integral and derivative terms affect the output. So let's move on. And what we're looking at here is the current being sent to a drive-by-wire throttle control motor. So in the case of a DC drive-by-wire throttle motor, the ECU is able to drive the DC motor both forwards and backwards. So we have a 0 point in our axis here, and we can see that we have the motor being driven both above and also below. Just wait for my laptop to catch up, and also below our axis there. Okay, so in our first example here, we have just purely proportional gain, and we've got no derivative. So what we can see here is in this part of our diagram, we have an error where we are below the target. So in response to this, the ECU provides a positive drive to our DC drive-by-wire throttle motor, so it's driving it towards our target. Now the problem with this system is, while with proportional gain only, as we get closer to our target, the error is getting smaller, so we can see that the current being sent to the motor is being reduced, but the ECU can't actually do anything about this overshoot because the current doesn't reverse and go negative until we've actually shot past our target position. So the ECU can't prevent that overshoot. It can only respond to the error that's there if we're using proportional gain on its own. On our next slide though, we've now added in our derivative element. And the derivative element is looking at the rate of change of our error. And what we can see here is as we're coming up towards our target, the rate of change of error is reducing. And what we can see here is this is a braking effect. So this time the ECU is actually able to reduce the current and drive the motor, the drive-by-wire throttle motor, in the opposite direction prior to us actually overshooting. So in this case here, you can see this section of the reversed current. This actually occurs before we get to this point here where the drive-by-wire throttle motor has overshot its target. So hopefully that's a little bit of an illustration of what's actually going on and how the PID control algorithm actually functions. Now what we're going to do is talk about the individual terms in a little bit more technical detail and explain what each of them is. And I think it's important to have both this real-world analogy as well as a proper description of the technical terms. So the first element we're going to talk about is our proportional gain. So as its name implies, this is the P element of our PID control algorithm. As its name implies, the proportional gain is proportional to the size of the error. So basically any time we have an error, the proportional gain will be relative to the size of that error. So this is gives us an instantaneous result, or an output is instantaneous anytime we do have an error between our target and our measured aspect. I'll just jump back into my notes here. So just as an example here, if, for example, again using our boost control analogy, if we had a target of 100 kPa and we had a proportional gain of 0.1% per kPa, then the result would simply be, so the result that's going to be applied to our control set point will be our proportional gain 0.1 multiplied by our error. So if we had an error of 100 kPa, 0.1 multiplied by 100, that's going to give us a 10% change to whatever is in our feed forward table. So that's how the proportional gain works. So in that example, if we were 100 kPa below our target, the proportional gain would add 10% to our wastegate duty cycle that we've got in our feed forward table. Now, one of the problems with the proportional gain, though, is using proportional gain on its own will never get us exactly to our target. We can never achieve a zero error. And the reason for that is that as we get closer to our target, the proportional gain becomes smaller and smaller, so it has less effect on our control, and we don't ever get to a position where we actually have a true zero error. Now, some tips with tuning the proportional gain. If we use a proportional gain that is too small or too low, we're going to end up with very slow control. It's not going to follow our target particularly quickly, and we're also going to end up with a large error between our target and our measured values. So again, an example of our boost control, we're going to get lethargic boost response, and we're also going to end up nowhere near our target. On the other hand, if we increase our proportional gain too far, we're going to get really quick response to any error. However, we're also going to risk having the system overshoot and oscillate and become unstable. I'm going to show you these terms in use really shortly. I'll just go through the other two before we get into that. The next term is our derivative. So we already know that this is like the brake pedal in our real world analogy. And the derivative looks at the rate of change of error. So it's looking at the rate of change of error over time, or how the error is changing, I should say, in respect of time. Now, this allows us to provide a damping effect on our control. And this is essential for us to be able to use a large amount of proportional gain and not end up with oscillating in an unstable system. So it's really important, particularly with our boost control example, we're going to be using proportional gain combined with derivative gain to get us that fast response that we get with a high proportional gain. But the derivative gain's there to dampen and slow down that response and prevent that overshoot as we're coming up towards our target. Now, to give you an example here with our derivative gain, if we had an error that was decreasing at a rate of, let's say, 10 kPa per second, and we had a derivative gain of 0.5, then the maths for that is just our rate of change, which was 10 kPa per second, multiplied by 0.5. So it's going to give us a result of 5%. So in this case, 5% would be removed from the value being produced by our feed forward table. So that's just an example of how that works. It's really quite straightforward when we understand the math behind it, and what we need to understand is in our closed loop control strategy, the final value being sent out to our wastegate duty cycle solenoid, our wastegate solenoid should say, is the sum of our feed forward, remember that's our base duty cycle position, our feed forward plus our calculated proportional, integral and derivative gains. And again, we're going to see all of that in action really shortly. Our last term is our integral gain, and this is a slower moving component that looks at the size of the error over time. And remember I said that with a proportional and derivative control alone, we can never achieve a zero error, because as we get closer to our target, the amount of the proportional gain starts to become smaller and smaller, so it has less effect on removing that error. So it's always going to leave us with some error, and the integral gain works to remove that error. So what it's doing is it's looking at the size of that error over time, and it's applying a positive or a negative trim to our duty cycle in order to remove that and reach our target. Now, because the integral gain, it works on what has happened, so the error that was present, what that can result in is it will end up with us potentially overshooting. So that is a problem, particularly if we use too much integral gain. And the sort of idea here is if we have too much, we're going to end up with unstable control, and again our system will tend to oscillate. And if we don't have enough, we're going to end up with a constant error where we're never quite going to reach our target. One aspect I will just mention here with integral gain is we can get into a situation that's referred to as integral windup. This is really common in any control system where a mechanical limitation perhaps stops us from being able to achieve our target. And a really common situation here is with cam control, where we are trying to target a cam position that we physically can't reach. So let's say that the mechanical limitations of our cam movement let us get to 40 degrees of cam advance. So if we target a value of 45 degrees, that's beyond our mechanical stop. And what's going to happen is the ECU will drive the camshaft hard against that stop. It's looking at our cam position and our target, and because it can't get to our target, there's always going to be a remaining error. What happens is the integral element continues to try and drive the system harder and harder to achieve our target, which we can't get to. And because it can't do anything about it, the integral element just continues to climb and climb. What this manifests itself as is when we drop back to a cam target that we can achieve again. So let's say our cam target now drops from 45 degrees back to 30 degrees. That integral element is wound up so high, it then needs to reverse before we can actually start tracking our target again. So this results in a really lethargic response to our cam target once we drop back into the sort of areas that we can achieve. Okay, let's have a look at some of these aspects in use now. So what I'm going to do is I'll just get our Toyota 86 started up on our dyno, and we'll jump into our laptop software here. So if Colin can just show the laptop, and I'll just get our fan running. Okay, so again, we're using proportional gain. We're using our boost control here as our example, and I'm on the boost control worksheet in our tuning workbook here on our Toyota 86 package. Now, I'm not really looking specifically at the intricacies of boost control. What we're only really doing here is looking at the aspects we've just talked about. And let's start with feed forward. We can see that here in our list. And if I click on feed forward, we'll see our table pop up here on the right hand side. And what I'll do is I'll just full screen this so we can see it. So what I've got here is a three-dimensional table. We have our boost aim on the vertical axis, and we have our engine RPM on our horizontal axis. So the numbers inside this table here are simply our base wastegate duty cycle values to get us close to our target boost pressure when we're in open loop. So for example, if we see here, and we're actually currently targeting 60 kPa gauge boost pressure, so we can see here that, for example, at 4,000 RPM, achieving 60 kPa of boost pressure requires around about 42% duty cycle being applied to our wastegate solenoid. If we move further through the table, we can see that at 7,500 RPM, that climbs a little bit, and now we need 50% duty cycle. So if this is properly tuned, what we should find is that even with no PID gains being applied, we should be very close to our target of 60 kPa gauge. Right, let's drop back down, and now we can see our three terms here that we've been talking about. We have our proportional gain, we have our integral gain, and we have our derivative gain. Now, a clue to all of these as well, if you ever get confused, is if we look on the right hand side, MoTeC give us the units, and this is a clue to exactly what this particular, each of these components is going to be doing. So for example, here if we look at the proportional element or proportional component, you can see that the units are listed, or the gain is listed at percent per kPa error. So again, if we had an error of 10 kPa, and our gain, which you can see here, we've got set at 1.0, we would end up with the duty cycle being affected by 10%. If we move down, we can see our integral gain is kPa multiplied by our time component, our seconds, and if we move down further, we can see that our derivative gain is percent per kPa per second, so rate of change of our error. Just a really good way of reminding yourself if you ever do get confused. Okay, so what we can do is just have a look at how these elements interact, and what I've got at the moment is something that's going to be able to show you how the PID system works. So I've got a proportional gain of 1.0. I've got an integral gain of 0.2, and I've got a derivative gain of 0.2. These work reasonably well for our Toyota 86. What I've done is I've purposely set this up so our boost control isn't going to be perfect, and this will let you see the PID elements in action. So what I'll do now, I'll get the car into fourth gear. During this dyno run, I'll get Colin to just focus on the dyno screen, and you'll be able to see our power in kilowatts as well as our boost pressure being displayed on the dyno screen in real time. So let's do that now. Okay, so that's our run complete there. I'll just let the car come back down to a stop. And what we've got on the bottom, we've got our green line here, which shows our power in kilowatts. We're not really that interested in that. What we are interested in is our top line. The red line is showing our boost pressure. So this is gauge pressure. You can see that I've put a little line through here, a white line at 60 kPa, which remember is our target. So we can see that initially our boost pressure between about 3.2 and about 4,200, 4,300 RPM. We're a little bit below our target, and then we can see that for the rest of our run we're actually pretty close. We probably drop off a little bit in the top end, but so we can actually see what's going on, let's just jump back into our laptop software. I'll full screen our time graph and we'll have a look at what we've actually got going on here. So let me just zoom in a little bit. Okay, so I'll just talk through what we've actually got being displayed on the time graph. So our first group at the top, we have our engine RPM, and you can see the area that we've just done our ramp run in there. We've gone from about 2,000 RPM through to about 7,500 RPM. Our next element is our turbocharger speed, which in this aspect isn't really that important to us. Moving down, we have our inlet manifold pressure, throttle position, and our exhaust pressure. Again, I'm not really that interested in these parameters for our example, nor am I interested in our lambda. What we've got though on our next graph here, our next group, is our boost aim, which is in blue, and our boost pressure, which is in green. Now I'll just point out again that both of these are being represented in gauge pressure, so any time we have a positive value, this is above atmospheric pressure. So we can see again our blue target is 60 kPa consistently right through our graph, and we can see that initially we're a little bit below our target, and then we climb and reach our target really nicely. Again, right on the top end we drop a little bit below our target. On our next group, what we've got is our boost control feed forward and then our boost control percent. Now these two show the input to the closed loop control system in terms of our feed forward. These are simply the values coming from that feed forward or our normal position table that we've already described. So remember, these values get us our open loop control. So we're going to get our boost control as close to our target as we can, simply using our feed forward table, and then the PID control's not actually going to have much work to do. The yellow line in this example though, this is the final duty cycle being sent out to the wastegate solenoid. So the yellow line in this instance, it is our feed forward plus our P, our I, and our D gains added together. So it's just simply the accumulation of all of those gains plus our feed forward value, and we'll see how that works mathematically really shortly. I'm just going to jump ahead a little bit and look at our bottom graph here, which is our boost control error. So this is really a key aspect of any closed loop control system. So remember, it's looking at the error between our target and our actual values, and then it's using that as the input to our closed loop control. So again, as we've already talked about, we are a little bit below our target at the start of our run, and then we achieve our target really nicely through the middle of our run, and then finally we drop back just a little bit below our target again at the top of our run, and the values are relatively small. We can see here at 7,200 RPM we're 2 kPa below our target. Okay, so now we've seen all of those aspects, let's see what the ECU is actually doing. And this is a really nice aspect of the M1 because we get to log and see exactly how the PID control algorithm is working. This is useful particularly when it comes to making changes and actually adjusting the PID gains, because we can see exactly how they're being applied by the ECU and what power they have over our output. Okay, so let's look at those, and right at the start of our run here, remember we're below our target. So we can see here our P gain, our proportional, which is in blue, is quite positive. We have an error, so our proportional gain is driving the system hard to try and reduce that error. So in this case, we have an error of 5.2 kPa. Remember, our proportional gain was 1. So 1 multiplied by 5.2 gives us a 5.2% adjustment that is then being sent out to this the wastegate solenoid. So all of these gains here, these are the final values that the system is going to be applying to our wastegate solenoid. Let's move further through the system, and we can see that through the middle of the system, our proportional gain now is 0.2. So we're very, very close to our target, and the proportional gain essentially is doing very little. Moving back to the start here, we can see that as we first come up on boost, we're ramping up onto boost. So we have two aspects going on here. First of all, we have a large error. We haven't got to our target, so we've got the proportional gain working quite hard to try and reduce that error. So in this case, we can see that as I'm coming up onto boost at 3,500 RPM, we have a positive proportional gain of 13.5%. At the same time though, it's important to understand that as we're ramping up towards our set point, the rate of change of error is an important aspect here. Our error is reducing quite quickly, so we also have our derivative gain, which in this case is minus 6.4, and that's working to dampen our closed loop control and stop us from overshooting. So we can see those two aspects being used there. Okay, and then if we look at our red value, which is our integral gain, we can see that that is sitting relatively constant at around about 2.4%. So that's helping there to reduce any error over time and try and get us closer to our target. If we move back up, we can see the yellow line here represents that final duty cycle being applied to our wastegate solenoid, and let's look at exactly how that might work. I'll just pick a particular point here, 3,900 RPM, and what I'm going to do is just bring up our calculator. So what we want to do is first of all look at the sum of our gains. So all I'm going to do is sum together our proportional, our integral, and our derivative components. So in this case we have 5.1, which is our proportional gain. We have 1.0, which is negative, which is our derivative gain, and then we have 1.6, which is our integral gain. So the cumulative effect of our closed loop system here, our three gains, is a positive value of 5.7%. That's going to be, remember, added on top of our feed forward value. So if we look at the feed forward table, our feed forward value at that particular point is 42%. So we'll add that in. It gives us a value of 47.7. We've got a small rounding error that's crept in there. The final value at this particular point is 47.8, but hopefully that illustrates the way that these three gains are working together. Alright, now what I want to do is just zero out these gains for a second, and what we're going to do is have a look at what happens when our gains are set too aggressive. So in this case what I'm going to do is I'm going to jump up to our proportional gain. In our example that I gave there, we didn't have perfect boost control. Wouldn't have been a great example of closed loop control if it had been perfect off the bat. I really wanted to show you what happens when we do have some error in there. What I'm going to do now is just set our proportional gain to a really high value, in this case a value of 8. So this is going to give, remember, a really dramatic effect to our wastegate solenoid duty cycle with respect to any error that's present. So I'll just unpause our time graph, and we'll again do a ramp run on our dyno. So let's just focus on the dyno here, and we'll see what the effect of our proportional gain, a very large proportional gain, is on our boost control. Alright, so we're ready for our second run. Let's do that now. Okay, so we can see this time our proportional gain alone hasn't given us particularly good boost control, and what we've got is this situation where our boost control has oscillated. So we can see it comes up and overshoots our target slightly, then our wastegate duty cycles dramatically reduced, and we can see our boost drops below our target, and then we can see it continues to cycle and oscillate up and down. So this is what we're going to end up with if we've got too much proportional gain. Let's just jump back into our laptop software for a second and we'll see the effect of that. I'll just zoom in a little bit. So we can see our boost control, first of all, our proportional gain being applied here. We're absolutely off the scale of our graph, and the aspect that's being shown there as well is the result of that on our actual boost control being sent to the wastegate solenoid, in this case 169%. So we're actually asking for all of the boost as much as we can. Then once the boost pressure overshoots, our control system pulls back down and reduces the boost pressure below to our minimum value as well. So this is what's going to happen. We're just constantly cycling between our minimum and maximum duty cycles that the wastegate's control system can achieve. What I'll do now is we'll just close that back down, and we're going to set our proportional gain this time to 0, so we've got no proportional element at all. What I'm going to do now is we're going to go into our integral gain, and I'm going to set our integral gain to a value of 1, which for an integral term is quite a large gain. And we're going to simply go through that process again, and we're going to do another run and see what the effect is on our boost control. So let's just jump in now. Again, we'll just go across to our dyno screen, just get into 4th gear and go back to full throttle. And we're ready for our 3rd run, so let's do that now. Okay, so we can see that with our integral gain alone, we actually achieve reasonably good boost control. We can see that our boost overshot in the mid-range, and then the integral elements kicked in order to bring our boost back down. And for the most part in the top end, our boost is actually pretty close to our target. Let's jump back into our laptop software and we'll see how that all looks in our laptop software, what the ECU actually did with that. I'll just zoom in again so we can see the area that we're really interested in. Okay, so we can see first of all our integral element being displayed here in red. So right at the start of our run, we have this area where we are below our target. We've got a positive boost control error, and the integral gain works in response to this error by increasing. And you can see that it continues to increase with time. Anytime that error is positive, the integral gain is increasing. Now we get to a point here where our error is essentially 0, or we've got half a kPa error, and we can see that at exactly this point in time, this is where our integral gain flattens off. Now the problem we've got though is that now, because our feed forward table isn't quite tuned correctly, now what happens is our boost pressure starts to increase and overshoot our target. This is being demonstrated by our boost control error going negative, and what we can see in response to that is now our integral gain starts reducing again, and we get to a point where essentially our boost control sits very close to a 0 error. So the integral gain, you can see this working again. It's in response to our error over time. Now I've shown you the proportional gain and I've shown you the integral gain. I can't really do any demonstrations with the derivative gain because really this is a dampening effect being applied to either of the other two gains when they're helping the system try and achieve our target. So hopefully that's given you some insight into the proportional, integral and derivative gains and how they work in action. We're going to move into some questions and answers very shortly, so if you've got any questions, please ask those in the chat box and I'll do my best to answer those very shortly. But what I'm going to do now is we're going to go over the tuning strategy. Now we've got an understanding of feed forward, how that works, and we've got an understanding of the proportional, the integral and the derivative gains. We're now going to go over a technique that we can use and apply to our tuning, and that's regardless of whether we're tuning closed loop boost control, idle speed control or cam control. Basically any time we're tuning a closed loop control system. Now, one thing I need to point out here is that PID or closed loop control is not going to fix a system where we physically can't achieve stable control. So it's limited essentially by the basic system. And what I mean by this is if we've got a boost control system, a wastegate installation where the wastegate isn't able to achieve stable control without any electronic intervention, we're going to really struggle to get good stable boost control using a closed loop system. So an example there might be where the wastegate fitted to the vehicle is too small and that's resulting in boost creep at high RPM. If we've got that using a mechanical installation, then there's no way that the electronic system is going to be able to fix that. Similarly, if there's a plumbing issue that's resulting in the pressure signal being delayed in being received at the wastegate, and this was resulting in overboost, again we can't fix this using PID control. So it's limited by the system. The mechanical system needs to be sound before we try and apply closed loop control, and this is an area where a lot of tuners will waste a lot of time and end up having a lot of frustration, is trying to fix a system that is mechanically flawed using closed loop control. It's simply futile. You need to go back to basics and fix whatever is wrong with your system to start with. Okay, so going back to what we've talked about here, remember we need to get our feed forward table tuned properly first. So this is our very first place to focus on, and what we want to do is actually begin by setting our P, our I and our D gains all to 0. Essentially this places the ECU into open loop mode. It's not going to make any corrections to our duty cycle if we've got an error, and then what we want to do is go through and adjust our feed forward table until our control is as close to our target as we can reasonably get. Now this is going to achieve two things. First of all, the closer we can get our control without any closed loop feedback, the less work the ECU has to do. It's going to have an easier job doing it, and the result for us is we're going to get better, more stable control out of the system we're tuning. The other aspect though is this is the perfect time for us to prove that the system is able to achieve good control without electronic intervention or without the closed loop intervention. So if we're struggling at this point to get repeatable and consistent control over our system, then this is the point where we need to stop and fix whatever's wrong with our system first. Okay, so now we've got our feed forward table set up, we've got our basics set up. Now we can move forward and begin applying our P, our I and our D gains. And what I generally do here, remember there is no magic set of numbers that you can apply to every system that you're tuning. The numbers that you need to use to get suitable control are going to be very dependent on what exactly you're tuning, be that idle speed control, a slow moving system, boost control, a slightly faster moving system, or perhaps drive-by-wire or cam control where we've got very, very quick movements. I generally suggest starting with a proportional gain somewhere in the region of about 0.1 to 0.5. It's going to give us a relatively small amount of gain that's going to let us see the result of the closed loop system without hopefully putting us straight into instability and oscillation. What we want to do anytime we're making adjustments to any of our gains, what we want to do, my technique is to start by doubling the gain that we're interested in. So if we've got a value of 0.5 for our proportional gain and we want to see what the result of doubling or of increasing that will be, rather than making a very small change of 0.1 perhaps, which we may not be able to actually see any real result, we're simply going to go from 0.5 to 1. If we don't see much a result from that, we'll double it again, go from 1 to 2, from 2 to 4, etc. So by making quite a dramatic change there, it lets us quickly find the sort of range where our system is working properly. And what we want to do is continue doubling our gains until we get to a situation where our system becomes unstable and starts oscillating. When we get to that point, we know we've gone too far, and then we can simply move back by halving whatever value we have in there at the time. So it's a really simple way of quickly finding the sort of range for our gains that's going to give us good control. In terms of our derivative gain, I'd normally start with a value there of around about 0.1 to 0.5. So normally a little bit less than whatever I'm using for our proportional gain. When we are adjusting our proportional and our derivative gains, it's important to have an understanding of what we're looking for. And that just references back to those slides that I showed you. So as we increase the proportional gain, we're going to get faster response, but we're going to end up with some oscillation. We can increase our derivative gain. That's going to dampen our oscillations, and it's a case of finding a nice compromise between fast response without too much oscillation or overshooting. And what you will accept here is really going to depend on the system you're tuning and exactly how fanatical you want to be about it. Finally, our integral gain, this is the element that we're going to add in order to remove any remaining error that we might still see. Generally, this is going to be quite a small value, somewhere in the range of perhaps 0.1 to 0.2. Remember what we're looking for here, I'll just go over it again. If our proportional gain is too high, we're going to end up with instability and oscillation. If it's too low, we'll end up with a large error, and we're going to end up with slow, lethargic response. When we're adding in our derivative gain, if our derivative gain is too small, we're going to end up with the system oscillating due to our proportional gain and being unstable. If our derivative gain is too high, we're going to end up with very slow lethargic response to our system, needless slow response to our system. Then with our integral gains, if our integral gain is too low, we're going to end up with a remaining error. If our integral gain is too high, again we can start introducing some oscillation and instability into our system. Now once we've got our system roughly set up and we think we're quite happy with the results of our control, what we then want to do is adjust whatever aspect we're controlling, be that boost or cam position. We want to request a change. So for example, what I might do is set up a run through on the dyno for boost control, where during the run I step from 60 kPa to 70 kPa and then back down to 60 kPa. And what we want to do is analyze the response of the system as we go through that change and see how closely it's matching our target. We obviously need to be a little bit realistic about our expectations here as well. And what I mean by this is it's impossible for a turbocharger to respond absolutely instantly to our boost request. So we're not going to end up with our boost stepping up like a square wave and instantly matching our target. We're always going to end up with a slightly smoothed off rise in our boost value. So that's important to understand. If we're trying to achieve achieve something that's unrealistic, we're going to end up chasing our tail and wasting a lot of time. On the other hand, with drive-by-wire throttle or cam control, these systems can respond much faster, so we can expect to track very closely our target position. The other key here is you need to data log what's going on with whatever system you're tuning, and look at how the system is responding anytime you make changes to those PI and D gains. And again, the M1 ECU is great here because we can visualize exactly what is happening with those gains and see how they are changing our output to, in this case, our wastegate solenoid. We can see exactly at each step of our dyno run exactly how the system is responding. So in terms of going through those steps, we should be able to very quickly work out the range of values that our system is going to respond to without becoming unstable, and then we can fine-tune that system so that when we ask for a change in boost pressure or cam angle or whatever, the system is able to accurately and quickly track our target. Okay, we'll stop there and I'll just jump into our questions. And again, if you do have any more questions, please ask those in the chat. Raisin is asked, I missed the first part of the webinar, but I was curious if you applied theories like the Ziegler-Nichols technique for PID tuning and actually had them work. Actually, that's a really great question, and that was an aspect that I had intended to talk about, so thank you for bringing that up. So PID, a lot of tuners think that this is some new invention that ECU manufacturers have produced, and it's simply not. PID control strategies have been used in industry for decades. They are nothing new, and as such there are mathematical techniques to come up with the gains to work for whatever system you're tuning, and the Ziegler-Nichols method is one of those mathematical ways of calculating your gains. Personally, after 15 years in the industry, I have never used a mathematical technique for PID tuning, and I think I speak probably for 99% of tuners out there when I say that the trial and error method that I've just gone through and explained, this is the technique that we are almost always exclusively going to use. But yes, there are mathematical techniques that are in existence. C. Marion has asked, on the MoTeC Platinum ECU, is the differential any different to the derivative control? I actually can't answer that for you off the top of my head now. As far as I'm aware, there is a derivative gain in the MoTeC. One aspect with the MoTeC that is quite unique is that their PID control uses raw values, which I've never found to be particularly meaningful when we're looking at the gains that I've just talked through. It's very easy in the MoTeC because we know that, for example, the proportional gain, we're talking percent per kPa error when we're talking about boost control, so we can very quickly work out exactly what's being applied. With the MoTeC, this raw value, it's not so straightforward. So I'm sorry I can't answer your question there. I will confirm that and answer in the forum though. Another question from C. Marion, who's asked, on the MoTeC Platinum ECU, are the boost control P, I and D channels in units of percent the same as the MoTeC M1? Again, I'm sorry, I can't answer your question here and now. One of the aspects with the MoTeC, because we haven't been using that on a boosted car here, my personal testing on it has been much more limited, so I will let you know in the forum. Barry has asked, have you encountered any PID systems that require a frequency rate set on the PID system? How do you go about achieving the correct frequency? No, I'm not sure here, Barry, if you're talking about the actual frequency of the PID control, or you're talking about the frequency that the control system is outputting at. So by that I mean a wastegate duty cycle. I'm going to assume, sorry, the frequency that the wastegate solenoid is being controlled at. I'm going to assume that you are talking about the actual PID calculations. Every ECU that I've encountered, that has not been a user controlled function, and that's been a hardware aspect that's been set by the engineers. So that's not an issue that I've come across. Just to really briefly talk about the wastegate solenoid frequency, probably getting a little bit beyond the scope of this actual webinar, is an important aspect to understand there. If our wastegate solenoid is being pulsed at a frequency that's either too high or too low, that's going to affect the control of the system. And again, really this comes back to what I was talking about, making sure that we can get good stable control and open loop first and foremost. Raisin has asked, is it worthwhile to mimic a step or a ramp input and analyze the response that way? Yeah, absolutely. To reiterate, that's what I was talking about, where we are asking for a change. So be that a cam position change where we might step between say 10 degrees and 30 degrees and look at the response as we step through that particular change, or the boost control change that I've talked about. We need to ask for a change and then analyze the response of the system to that change. Particularly with boost control, while obviously as the system ramps up onto boost, we've got a large change in error over a relatively short period of time. Once we've actually reached our boost threshold and the wastegate is open and controlling boost, we're only really moving gradually sort of up and down around our target. So there's not a huge amount of work for the PID system to do, hopefully, once we're actually in that control range. That's why we really need to make the system work and ask for a change in our target. Adams asked, any pointers for cars that overboost after throttle liftoff and immediate application? Would increasing the boost control activation pressure help, e.g. a sequential transmission shift? Look, that's a really common problem. It goes a little bit beyond the scope of this particular webinar. We're not really looking at specifically boost control, but one of the aspects, and I do deal with this in detail in the boost control course, one of the aspects that's really important once we've got our closed loop control functioning is to test the system in a real world condition. And this is an area that I know a lot of tuners would overlook. We get really nice stable control of our boost during a ramp run. We take the car out on the road or the racetrack, and in situations where the driver is cycling in and out of the throttle rapidly, which is often the case mid-corner or on a gear shift, that's when we start seeing the overboost. So there are a range of control strategies to deal with this. Often this happens, I find, when we have an overly aggressive proportional gain, or likewise a derivative gain that is too low. Now on a ramp run we can probably get good control even with these P and D components being non-optimal, because we can get our control really close as the engine ramps up onto boost using our feed forward table, but those strategies start to show up that they're not optimal when we are in and out of the throttle on a gear shift. Now if we go through that system of asking for a change in boost during the run, or alternatively we're actually on the dyno in and out of the throttle, we're very quickly going to see that we have a problem, and we can address that in our tuning at the time. Okay, that's brought us to the end of our questions. Hopefully that's given you some more insight into what the feed forward table is, what the P, I and D gains actually represent and mean. Remember that real world analogy is a great way to remember what those particular components of our closed loop control system are doing, and then hopefully also some insight into a strategy you can apply in your own tuning for setting up closed loop control. As usual, if you've got any further questions, please ask those in the forum and I'll be happy to answer them there. Thanks for joining us, and we'll see you all next week.